Okay, just wanted to show you on a live working circuit how resistance is effectively invisible unless you have an operating circuit. So unless you're doing a voltage drop test, if you're doing an open circuit voltage test, you will not see resistance in a wire, so like a wire that has high corrosion in it or something like that. So in order to demonstrate that, we've got a series circuit here with just two bulbs in it right now. We have our power supply, obviously. So we have a red wire coming in from our power supply over to our first bulb, comes out of our first bulb through this red wire to this terminal right here, which then goes through our second bulb right here, through this black wire, and back out to the ground of our power supply. And you can see if we turn that on, we have our power supply set to 12 volts, and this is a little janky. It's an older board, but there we go. We got two bulbs that are lit up. We're drawing 1.36 amps or so, right? And we turn this off. Now, I can measure the resistance through this bulb and show you that. Let's take this out. It is a bit wonky. Again, this is an older board. It's an older setup just in general, but we got roughly 2 ohms-ish, if I can get a reading, right? Around 2 ohms or so through this bulb. So the electricity has to come from here, through this wire, through this bulb, right? Drops a certain amount of voltage based on the resistance in there, through this wire, which shouldn't have anything on it. If we measure it, if we remember from discussions previously, a wire should have very little to no not zero, but very, very little resistance in it. Again, these connections are a little bit wonky, so that's a bit high, but still not too terrible. So we come through that wire, through our bulb, and then back out to ground. Now, if we, let's say, are working in the, so we know, let's recap here real quick. We know that we have a resistance in series with this bulb. So there is something. If we're imagining ourselves on a car and we're just trying to diagnose why this bulb is not lighting up, if we imagine this bulb is corrosion, it kind of explains, sort of, why we wouldn't have a bulb that is super, super bright. If I take this out, can I do this easily? If I take this out, replace that, we got a real bright bulb, right? So we have two bulbs in series. So we can look at this bulb as corrosion. So if we were to and I can't really demonstrate here corrosion exactly because these are bulbs. It's a manufactured resistance, right? But we can measure, so let's say we came along here. Actually, let's leave this on. Let's say we're working on the car. This bulb's real dim, and we want to see why, right? Well, the first check a lot of people do is they'd be looking for voltage to this bulb, right? They want to see, well, do I have 12 volts at the bulb? So I've disconnected, imagine this is like an automotive connector. I've disconnected our bulb, right? Put my multimeter red probe, doesn't matter really, on power. Put this, we'll say we're going back to the battery. Measure this, the battery voltage, make sure we're in voltage. Can't measure resistance, or I can't measure voltage with resistance. Go to battery. So that is a pretty standard check you do in the car, right? Do I have 12 volts there? And you do. You can see on the meter, we have 12 volts, but that's not a real 12 volts because we know that this bulb is in series with the circuit. So all the electrons have gone through here, through this bulb, and are building up at this wire. We have the potential to do some work. We have 12 volts of potential, but we're not actually doing any work. We just have the potential. One way you can kind of imagine it is if you have a bucket. You have a bucket, it's full of water. You have a tube coming out the bottom of the bucket with a little water wheel, let's say, in that tube, built into that tube, with another tube coming out the bottom of the water wheel to ground or to another bucket or whatever. And you can imagine that if you are holding the bottom tube, right? So the entire tube's full of water, the water wheel's full of water, the bucket's full of water. If you're holding the bottom tube, you're not getting any flow. You're not getting any flow, but you have a certain amount of pressure built up in that. Not a whole lot, it's a bucket, right? But you have a certain amount of pressure built up in that system ready to go. And then if you are to open your hand at the bottom, you've now created a path for electricity, in this case water, to flow. The water wheel will start spinning and some work will be done. Now, if you have a water wheel that has really, really good bearings in it, you're going to get like skateboard bearings or something that can spin really, really easily. You're going to get a decent amount of flow out of that tube assembly with the bucket until it runs out, obviously. If you have a water wheel that has really, let's say, gummy bearings that are all rusted up or whatever, and it's hard for that wheel to spin, you're going to get less flow, less amperage, right? That's where Ohm's law and water, why they kind of work together, because when resistance goes up, amperage goes down, right? In this case, our flow of water will go down. So if we have sticky bearings in there, we're going to have less flow, less amperage. Same thing applies to here, to our scenario in front of us. We had 12 volts of potential. We have 12 volts of pressure. Once we make a circuit, we're starting to flow, but we're dropping some of that voltage, right, through this resistance. So if we were to measure now, at the top of this bulb, what is actually available to the bulb in real life is 6-ish volts, right? 575, 6 volts. So we've lost 6 volts. And this could be a bulb, this could be, well, in this case it's a bulb, but in the real world, this is corrosion. This is what corrosion does. Corrosion is taking a certain amount, in this case 6 volts, a certain amount, it's the same measurement, a certain amount of voltage away from the circuit as a whole. So this bulb, all that's left for it to do or use is around 6 volts, so roughly around the same resistance. Those are series circuit rules. So that's all it has. That's the only push it gets to push that amperage through there is 6 volts. So it's going to be dimmer. In a correctly operating circuit, if we take this bulb out completely and replace it with this bulb, you see it's super bright because there is no resistance. There's nothing pulling away from our circuit. All we have are these wires that shouldn't be dropping a whole lot. And as a result, our one bulb gets to drop or use the full voltage, which is why it's so bright. It gets, big push, a lot of amps in there. Wow, 1.9, it's kind of hard to see, almost 2 amps, right? So it's a really bright bulb. Now, if you swap it around, our resistance goes up. As a result, our amperage goes down a little bit, right? So both bulbs have to share. Both bulbs are going to reduce in amperage a little bit. I'm really blinded right now. And they're going to be dimmer. And this is a real good example of why a voltage drop test or a live voltage test is so important in electrical diagnosis, because this voltage that you're seeing here, this open circuit voltage, I like to call it, it's not real voltage, right? It's not, it's a good check for opens and shorts to ground, because you have the potential to do some work, but it's not real voltage. You have to also then double check that your circuit can actually continue to deliver the 12 volts. And there's a bunch of different ways that you can check for it. We've talked about them already. But this is something to take into consideration when you are diagnosing electrical faults. Hope that helps. I'll see you later.